Um, your class has been about virology from the point of view of microbiologists and virologists. What I'm going to do today is turn the tables a little bit and talk about control of viral diseases from a public health point of view. Hopefully, most of this will be very familiar to you. And as a matter of fact, had I given this lecture to you 4 years ago, a lot of this would have been perhaps new to you, but having lived through the COVID pandemic for the last 3 years, a lot of what I'm going to be talking about for the next hour or so in terms of control of viral diseases will be very familiar to you. But we're going to run through some basic virology, talk about the various means of controlling viruses, looking at vaccination and immunoprophylaxis, looking at antiviral agents, and then looking at some issues in terms of obstacles to the control of viruses and ways to improve that control, and then talk about a little bit about the relationship of viruses to cancer, and then talk about virus control in the context of what we've been living through for the last 3 years in the COVID pandemic, and also a little bit about COVID-19 and HIV interactions. I'm going to talk for about 40 minutes or so. We'll have a bit of a break, and then we'll continue on for about another half hour and hopefully have plenty of room for questions. I'm sorry I got here a bit late. I had in my book that the lecture was starting at 11:30, and I was just reminded by your class rep that it was actually 11. So sorry for those of you who have been waiting around for the last 10 minutes. Anyhow, to begin, most of the next few slides should be pretty familiar to you. Just reminding you that viruses are very small infectious agents made up of a piece of genetic material such as DNA or RNA. They invade cells in the body. They use the components of the cells to help themselves multiply, which usually damages or destroys the infected cells. And many, or in fact, most viruses do not cause any harm or disease in humans, but those that do are the ones that concern us. Once the daughter viruses break the cell and spread elsewhere, if a host's immunity operates effectively, the virus-infected cells will be killed, leading an interruption to the virus cycle. But this is not true of all virus infections, because as you're aware, for example, with HIV, viruses may persist in the cell without damaging it and make the cell a carrier. But the patient may look to be cured, but the infection persists and could spread to others. But most importantly, viruses cannot exist on their own. For survival, they need to spread to another host, either a human host or another animal host, or even a plant host, but they can't live on their own. And again, this has probably been familiar to you through your class notes, that viruses can be spread in a number of different ways, through skin contact, such as the HPV virus, which causes warts. A number of viruses, including COVID, can be spread through respiratory route, but also that includes measles and mumps. The fecal-oral route, which spreads polio, echovirus, Coxsackie, hepatitis A, breast milk transmission, most importantly, HIV and cytomegalovirus. It can be transmitted transplacentally. HIV, another example here, as well as CMV. HIV also an example of sexually transmitted viruses, but that can also include HPV, hepatitis B, and Zika virus. And then, of course, insects can transmit viruses such as yellow fever, dengue, and as well animal bites such as rabies. So a lot of different ways that viruses can be spread and transmitted. Here's a little chart showing you the routes of transmission. There has to be a susceptible host. That can be an elderly or infants or anyone, especially if you're immunocompromised. The virus is there as a reservoir. It can be in people or animals or soil or food. It gets transmitted by coughing or body secretions, feces, or other human transmission sexually. And it could be direct contact or indirect contact or through vectors, and then coming in through the mouth, the nose, the eyes, other portals in the body. This route of transmission hopefully has been, you've seen this before. In terms of animal reservoirs, again, a large number of animals can be reservoirs for viruses that affect humans. So, for example, influenzas in birds, pigs, and horses. Rabies can be found in bats, dogs, or foxes. Lassa and hantaviruses in rodents. There's still some question as to where Ebola and Marburg viruses reservoir, whether it's bats or monkeys or some other primates. We've seen historically that HIV-1 and 2 probably came to humans via chimpanzees or other primates. Newcastle disease in poultry, West Nile virus in birds. COVID-19, as you know, the jury's still a little bit out whether there's an animal reservoir, and if so, which animal is it? Suspicion is pointing towards caves in southern China, where perhaps the virus originated, but nothing has been proven on that yet. But definitely animals are a major source of reservoir for viral diseases, which of course, as you can understand, makes it much more complicated to try and control some of these viruses. Again, this is hopefully all fairly familiar to you about the normal response to virus infections, that the first line of defense is the innate immune system, either adaptive immunity, which produces antibodies and creates humoral immunity, and the antibodies which are produced are either IgM or IgG, and the second line of defense being cell-mediated immunity, which involves killer T cells that recognize suspicious viral fragments and destroy the virus. I certainly hope that none of this is unfamiliar to you by this point in time in your medical learning. So to get to control can have a number of ways. We can actually prevent the infection from happening through vaccination or environmental control measures that avoid contact. We can mitigate by trying to reduce the transmission through isolation, quarantine, and social distancing. This should ring a bell as far as COVID is concerned. And then, of course, there's treatment with antiviral agents. But there's no magic bullet. As I noted, there are thousands of viruses, hundreds that can cause disease in humans, ranging from trivial infections that you barely notice to plagues or pandemics that alter the course of history. There's no single magic bullet approach to control, partly because the various modes of transmission for viruses, the various pathogenicities of the various viruses, human behavior. Vaccines over the last 200 years have probably been the most spectacular progress that we have made to control viral infections. But vector control, sanitation have all contributed greatly. And over the last 30 years or so, there have been the development of a number of actual antiviral agents that are now available, including some for some very serious infections. I'm going to go through over the next little while a number of topics of ways of controlling virus infections, looking at them in more depth. But these include quarantine, import controls, travel restrictions, notification. Slaughter does not apply to humans, but you will have seen examples of, for example, herds of cattle that are slaughtered because they arrive in the country with foot and mouth disease. Decontamination, isolation, treatment, vaccination, and environmental modification. So let's look at each of those in a little bit of depth. This is sort of the same chart that I showed you a few slides ago, but with the various control measures put in. So you can see the various places on the portals of entry, portals of exit, susceptible host, where these various control measures can have some effect, whether it's aseptic technique, hand washing, isolation, disinfection, various places along the chain. There are many places along the chain where these control measures will break the chain of infection. So quarantine, as its name suggests, is when you separate the infected persons who have signs suspicious of an acute viral disease from others, whether it's a rash or having received a positive test. And I don't have to explain this any further. I'm sure a few of you, or more than a few of you, spent some time in quarantine over the last 3 years because of having COVID or having been exposed to it. Import controls, as I mentioned a couple of moments ago, this applies mainly to animal imports, but it also means restricting international travel. And again, we all sat through several months of restricted international travel as a way of trying to reduce COVID-19 spread. Notification. In most countries of the world, certain diseases are notifiable. If a doctor sees a patient with HIV or measles or mumps or COVID-19, they are supposed to report that to the public health authorities. And these authorities, then the country informs the World Health Organization. And by this way, the world keeps track of infections and epidemics or beginning epidemics. The problem with notifiable diseases is that this depends on individual physicians or clinics to notify the authorities when they've diagnosed such a condition. And sadly, this doesn't happen all the time. Decontamination, again, not unfamiliar to any of you, washing and disinfecting your hands, clothing, and equipment after exposure, disposing of dead bodies in a safe manner, treatment of wastewater, chlorination of mains water, personal hygiene as a way of reducing spread of infection. And some isolation. This is different from quarantining, but for those of us, those of you who weren't able to attend funerals or weddings or go to church for several months, this is where this control measure comes in. Avoiding exposure to the virus, of course, is the first step. So, for example, for HIV, you've all heard the lessons about HIV control, reducing the number of your sexual contacts, wearing a condom, various protective measures. Donated blood is supposedly tested for viruses such as HIV and hepatitis B. Improving sanitation to reduce fecal-oral transmission, to prevent transmission of viruses such as hepatitis A. Control of non-human viral reservoirs. This is a bit of a controversial topic. In some countries, stray dogs are routinely slaughtered to reduce transmission of rabies. Quarantining incoming pets, vaccination of animals, testing imported livestock are all measures to reduce the spread of animal-related viral diseases. And avoiding contact with blood, body fluids, or tissues, basic sanitation techniques that you will be using when you start your clinic work. Vector control. As we noted earlier, a large number of viral infections are transmitted by insects, especially mosquitoes, such as yellow fever, dengue, Zika, West Nile fever. Reducing the vector populations does have value, and techniques which have been used in the past and are still being used include draining swamps, applying insecticide, screening homes, using insect repellent bed nets or protective clothing. But of course, it's now recognized that there are consequences to indiscriminate environmental changes. You may do some spraying and kill all the malaria mosquitoes in a neighborhood, but you're probably killing a whole bunch of other insects and maybe causing some problems for the birds who are eating those insects, or maybe causing problems for the humans that maybe have allergies or reactions to those various environmental agents. So it's a controversial topic and requires some areas of balance to reduce contact with the viral containing insects, but not causing too much damage to the environment. I'd just like to talk a little bit for a few minutes, and again, hopefully remind you about the various ways that we can produce active immunity against viruses by stimulating the immune system. There's active immunity, such as vaccination, or passive immunity, which is a bit more short-acting. One way to acquire active immunity is to survive infection with the disease-causing organism. Most of the time, if you've been infected by a virus, once you recover, you'll have lifelong immunity to that disease, or at least to the strain that infected you. This, of course, is important in influenza and COVID-19 because of the various strains that are circulating of the virus. And so you may have immunity to one, but not to another. Because following exposure of the immune system to the antigen, certain cells, memory B cells, circulate in the blood for many years. And when the antigen recurs, these memory cells replicate, produce antibody, and establish protection. That's the natural way. The other way, also quite natural, is by vaccination. So vaccines can produce a similar immune response so that many vaccines, once you're injected once, you have a lifelong immunity, or perhaps you need a booster. And COVID is an example of that as well. So administering a virus preparation that stimulates the body's immune system is an active viral vaccine. So we have attenuated live virus vaccines, we have killed virus vaccines, we have recombinant produced antigen vaccines, a number of vaccines, all of which work to produce this active immunity, which evokes the antibody response and stimulates the T lymphocytes when the body sees the antigen again. Vaccine effectiveness is assessed in terms of the percentage of the recipients protected and the duration and degree of protection. And an effective vaccine would protect more than 90% of recipients and produce fairly durable immunity. This is in contrast to passive immunity, which is conferred when you administer antibodies from another host. These are immunoglobulins. They are usually produced to protect individuals to a specific disease and usually are only used if you've been exposed. You then get a dose of immunoglobulin for that disease to hopefully protect you. Back to vaccines, there's the live vaccine and the inactivated vaccine. And most of live attenuated vaccines are produced by modifying a disease wild virus in a laboratory, and the resulting vaccine retains the ability to replicate, produce immunity, but usually does not cause illness. Inactivated vaccines can be composed of either whole viruses or fractions of them, and they can be either protein-based or polysaccharide-based. I'm assuming that most of this information you have already seen, and I'm just reminding you of it, so I'm going through it fairly quickly, which I hope will be okay. If this is all new to you, don't worry. I will be sending a copy of this presentation to your class after the lecture. So I hope I'm not moving too quickly for you at the moment. Killed polio vaccine. This is like 70 years ago. Was one of the first of these kind of vaccines, which really revolutionized vaccine technology. Now, 70 years later, we have a live polio vaccine, which is even more effective than the killed one. The word attenuate may be unfamiliar to some of you, but it's sort of the way that vaccination all began, by finding a weakened variety of the virus and then injecting it into the human to produce some kind of immunity. This began 300 years ago with the beginning of the smallpox vaccination, which was probably the first vaccine that was ever produced. And then in the 19th century, Pasteur and colleagues developed attenuated vaccines for anthrax in sheep, and then rabies in animals and humans. And this also played a role in some of the early vaccine development against tuberculosis and also human rotavirus. So most virus vaccines contain viruses that have been attenuated by laboratory manipulation. And some of these often confer lifelong immunity. There's a possibility that they may revert to a more pathogenic form. And so things have to be watched very carefully. But with the newer recombinant technologies, this is making these sort of things much less likely. Some of the problems with live vaccines is that a small percentage of recipients do not respond to a vaccine, and a second dose is recommended. There are occasional severe or fatal reactions to a vaccine, usually only in people who are immunodeficient. For most people with a sound immune system, these sort of severe reactions very, very rarely occur. And sometimes the immunity does not develop because of interference from a circulating antibody. This may or may not interfere with the replication of the vaccine and lead to a poor response. And live vaccines, this perhaps is the most important part of the slide, is that live vaccines are fragile. So they have to be kept very well controlled under controlled temperature conditions. They can be destroyed by heat or light. You'll recall the issues with the COVID vaccine, that the first vaccines needed to be kept at minus 70 degrees, which made them a little bit less portable and convenient to use. This changed later on, but the issue of the vaccines remaining potent because they've been kept in a stable temperature environment is a very important issue in terms of mass vaccination. Killed vaccines cannot cause infections, but they usually don't produce lifelong immunity. So additional doses are usually required. And sometimes because killed vaccine does not multiply, the inoculum itself sometimes has to be very large. So you need a fairly large dose of the vaccine in order to get any kind of immunization from it. And in more recent years, there's been the development of recombinant DNA vaccines, which have been developed against hepatitis B. And even more recently, the COVID-19 vaccines, which were developed through the mRNA techniques, has opened up a whole new field of vaccine development. We're just starting to hear about it now, but I suspect that you will see over the next few years the development of a number of new or at least improved vaccines as a result of the application of the technologies that were used to produce the COVID-19 vaccine. But as you can see, of those various vaccines that I talked about from over the last 300 years, the development of vaccines against various diseases, and you can obviously see the vast developments in vaccine technology that developed in the second half of the 20th century after the development of the polio vaccine in mid-century. So that we now have vaccines for a number of diseases that to the extent that polio has almost been eliminated. Most children these days do not get measles or mumps or rubella, which was a very common thing when I was a child decades ago. And a number of other diseases such as hepatitis B, for which there was no cure, there is now a vaccine as well. And in more recent years, we've seen development of other vaccines for rotavirus, zoster, HPV, and of course, in the last couple of years, the development of a COVID-19 vaccine, or actually several COVID-19 vaccines. And for those of you who are skeptical about vaccine, here's a fairly obvious reason why vaccine is important. Here we have deaths from diphtheria 100 years ago. I suspect that few of you might ever see a case of diphtheria in your clinical practice. Here's polio, 1955, the vaccine result. Similarly with measles. The fact that measles is recurring, we're seeing cases of polio, is because of people who are skeptical about vaccines. For those people who are skeptical about the necessity of vaccine, you would show them this chart. And they may say, well, that's very good, but I personally don't want to take a vaccine. Well, the reason that this works is that the entire community is getting vaccinated. If, public health, there's a point where personal liberty and public health collide. And I think that one of those places is in the control of viral diseases. But I'll get off my soapbox now about that. I'll be talking about it later. But of course, mandatory childhood immunization is now practiced in many countries because of this very nature of the fact that vaccination does prevent disease. And many other countries, even if it's not mandatory, they carry out routine vaccination campaigns to ensure that as many infants as possible are vaccinated. And international agents are monitoring immunization coverage, the development of testing on new vaccines, and the occurrence of outbreaks, so that when something like a new epidemic breaks out, such as COVID-19 or SARS or MERS or Ebola, countries are alerted and control measures can be set in motion. I had mentioned passive prophylaxis a few minutes ago, and just to remind you that these immunoglobulin preparations are recommended when exposure has occurred or expected to occur very soon, if there's no vaccine, or if there's an underlying illness that may make things even more complicated. Although once derived exclusively from animals, a lot of these immunoglobulins are now manufactured from human sources. But there are a variety of immunoglobulins. As you can see, this is just a few of them, but you can see they're used for post-exposure prophylaxis, for therapy, for passive immunization, for renal transplants. They have a place, but the thing about the passive immunization is that it's quick acting. There's a producing immune response within hours or days, and it can override a deficient immune system. The problem with passive immunization in immunoglobulins is that it's expensive because it requires hundreds or thousands of human donors or animals to get enough for a dosage. There's a possibility of allergic reactions. It often requires IV, intravenous administration, and it's a very short-lived immunity. It doesn't lead to long-lasting immunity such as you get from active immunization. So just to show you, here we are. Here's the level of antibody conjugation. With a passive immunization, you get an immediate high level of antibody, which drops off fairly quickly, as compared to active immunization, where you get the initial injection, you get boosters, but then you get active immunization that lasts for a very long time. New trends in passive immunization includes the use of monoclonal antibodies. These are still in their fairly early stages, although there are some very positive signs, but you'll probably be running into those more and more over the course of your clinical practice in years to come. And then we come to the other antiviral agent, which has been developed over the last 30 or 40 years, and that is antiviral chemotherapy. They attack viruses and kill them, they can be used to disinfect the environment, to sterilize biological products, or for antiviral chemotherapy, or elimination from virus from products. You may have received some antiviral chemotherapy for topical treatment of warts, for example. That's an antiviral agent that you're taking. Antiviral agents are not as effective as some other antimicrobial agents. And there are some, various using genetically modified technology, you can specifically target sites for antiviral agents. And this is most seen, of course, in cancer chemotherapy. But over the last 30 years, a number of antiviral agents have been produced against a number of diseases. And I won't go through this chart line by line, but for example, here are the various antiretroviral agents for HIV that have been developed in the last 30 or 40 years. There's the antiviral agents for influenza. There are medications that you can take for herpes simplex. All of these agents didn't exist 50 years ago and have been developed over the last few decades. And as well, interferon type agents can also be used to add into normal cells, protect them from viral agents. Recombinant DNA technology has led to the production of interferons and the subsequent conduct of extensive clinical trials. Again, this is still early days, but there has been some limited success. And I think you will find, as you enter into your clinical practice over the next coming decades, interferon type agents or agents that are related to interferons will be used more and more as antiviral agents. So combination therapy, the use of multiple drugs, you will see this, for example, in HIV, where a person can take 2 or 3 different antiretroviral agents to combat the disease. And it's been found that some of the combinations reduce the drug resistance, or you can use lower doses if you use combination agents. New drugs are constantly being searched for as antiviral agents, and they're, as you read the medical literature, every month or every issue of every magazine you'll read, we'll be talking about some new agent that's undergoing clinical trials. Most of these agents probably won't see the end light of day, but that's what drug companies do, and various research companies do, looking for new agents, not only to attack viruses for which there is no agent, but also viruses for which the current agents are becoming less effective or resistance is developing. I've gone through quite a bit of material in the last half hour or so. I see a number of comments in the chat. I think if anybody has any questions, you can ask them now. Otherwise, we can take a little bit of a break. But let me see what the comments are. Bit of controversy in the class about vaccination. We could talk about this for a while, but I would disagree with one of you who said that a vaccine has never been compulsory. I'm afraid that's not true. Vaccines have definitely been compulsory in many countries in the world. Measles, mumps, rubella vaccine in infants are compulsory. Polio vaccine is compulsory. For many years, travelers to Kenya or most other countries in sub-Saharan Africa, it was compulsory to have a yellow fever vaccination, which is still in the books of many countries. So don't pretend or assume that the regulations with regard to COVID are something new. They've been following in public health tradition over the last 100 years. As the person who wrote, "It's not about personal liberty, the safety of others should always come first," is exactly the point. What we're talking about with vaccination is not protecting not only you and your family, but protecting the community. So it has to do with protecting your neighbors, which was the same philosophy that we had with mask wearing. You weren't necessarily protecting yourself against COVID, you were also protecting your neighbor or the people you were passing by in case you were a carrier of COVID. So this is, of course, a very controversial area. I'd be prepared to have an argument with any of you who are anti-vaxxers, but I would hope that as medical students, there are no anti-vaxxers in the audience. If you're an anti-vaxxer, I don't think you have a place in medical science. But again, that's my own opinion. Anyways, let us take a break now. It's 11:45. Let us return at 12 noon. Have a nice break, and we'll see you in 15 minutes. Over. Okay, everyone. Back from our breaks, let us continue. For the next little bit, I'd like to go into more detail on the more complicated or more various aspects that are obstacles to control of viruses. These include poor infrastructure, global transport, mutation, vaccine design, reservoir hosts, rumors about vaccines, unsatisfactory vaccines, a number of various issues that we'll talk about in more detail. So, for example, again, poor infrastructure, something that, again, most of you are probably familiar with, because in Kenya, there are places in Kenya where there is a poor infrastructure. So if there's a shortage of infrastructure to enforce the controls of human or animal viruses, of course, during conflict and natural disasters, diseases spread when hygiene and people are hygiene is affected, people are put into camps, urban poverty and crowded conditions, making isolation and social distancing impossible. Another example from the COVID-19 pandemic. And as you will have seen, both in Kenya and in other countries, many countries during COVID, exposed the fact that many countries lacked the infrastructure and resources to handle the necessary public health measures needed to contain the pandemic. Global transport, with the increase in global transport and air travel, there are a lot of reasons why HIV may have been a very localized infection in Central Africa for dozens or hundreds of years until people started traveling. We all saw how quickly COVID-19 spread from China in December of 2019 to the rest of the world within 6 months. Tainted animal products being transported. So global transport is definitely an issue in terms of trying to control viral infections. Viruses mutate. And again, we have examples of this from COVID-19. For those of you who keep track of influenza, a new vaccine comes out every year based on what last year's influenza model looked like. So there, influenza is an example of a disease, of a virus that mutates very rapidly. And so things have to be kept very in close check to monitor mutations and changes in the virus. Reservoir hosts and insect hosts. Obviously, it's impossible to control dogs or bats or foxes or wild animals that are reservoirs of disease. Just as well as we said earlier, it's impossible, to kill all the mosquitoes. That a reservoir will always be existing there, and all you can do is try and reduce the contact between that reservoir host and your human susceptible person. Vaccine design. HIV is a very, very good example of a virus that people have been working on for the last more than 30 years to try and develop a vaccine, and they have not yet succeeded. And then there are other virus vaccines that are only particular against a particular strain of the virus. And again, influenza is an example of that. Rumors about vaccine. This is where we where the vaccine rumors, especially about COVID, but about other vaccines occur as well. And the internet has not helped the spread of these false rumors. Autism from the mumps, measles, rubella vaccine, not proven. Infertility from polio vaccines, not proven. All of the various rumors about COVID vaccines, ranging from sterility to microchips being hidden in the vaccine, all not proven. But those rumors are very powerful, and you can see examples all around the world of the effects of these false rumors, people believing these false rumors and spreading it, resulting in fewer people than needed being immunized against a vaccine. And then again, there are counterfeit vaccines, vaccines that don't contain the proper doses, or vaccines that, quite frankly, don't work. You've probably been reading as well, the Chinese COVID vaccine, unfortunately, is not very good. And countries where the Chinese vaccine has been used have not had as good a success rate against COVID as other countries that have had used more effective vaccines. And then there's the case of homeopathic vaccines. Don't get me started about homeopathy. There are a lot of people who swear by it, but there are not a lot of controlled clinical trials demonstrating the effectiveness of homeopathic vaccines. Sorry for all of those in the audience who are believers in homeopathy. But let's turn now to ways to improve the control of viruses. So we can do that by a number of ways. More vaccine coverage, which we've been talking about, new vaccines, better hygiene, cheaper vaccines that are easier to administer, better reporting so that we can keep track, modeling the effects of the vaccine or the effects of the virus infection, cheaper antiviral agents, more global cooperation and communication, all of which will have an effect on improving the control of virus vaccines. More vaccines, more vaccine coverage. There are several ways that this has been, that people are approaching this. Increasing or improving the number of vaccine programs that are happening, improving the coverage of the vaccine programs that do work, for example, measles, mumps, and rubella, increasing the amount of rabies vaccination in areas where there's higher prevalence of rabies infections, or expanding the amount of vaccine being produced. There were a lot of announcements in the past couple of years about increasing vaccine production, especially for COVID vaccine in Africa. There was a rumor that there was going to be vaccine production in Kenya. I'm not sure if that's actually happening yet, but it's certainly the intention is there. Developing new vaccines. We're still waiting for the HIV vaccine. We're still waiting for a good vaccine against dengue. And needless to say, there are other diseases as well that we're waiting for a vaccine or a better vaccine. Improving community hygiene, obviously, to reduce the spread of viral infections. Better hygiene, better sanitation to reduce the spread of hepatitis A. Discouraging intravenous drug use and unprotected sex to prevent HIV. Better housing, better clean water, better nutrition. All of those will help to fight against viral infections. And of course, better vaccine. Cheaper vaccines, less loss by heat, easier administration. All of those are techniques that will be effective in reducing viral infections. Better reporting and feedback. More diagnostic and surveillance teams in place to inform the vaccine manufacturers of how many doses to make. More reporting of side effects. Better public health reporting to keep track of infections and epidemics when they occur. Also, better health education to the public, to both not just to the general public, but also to physicians, veterinarians, etc., as to how to recognize signs of new viral infections that are developing. Mathematic modeling in departments of health to determine the best vaccines, when to administer a vaccine, have a vaccine program, areas of the country that one should target, certain populations that one should target, all of which will come from better data and better modeling from that data. Cheaper antiviral drugs. Of course, this is an example. For those of you probably don't remember because you're probably too young, but back in the late 1990s and early 2000s, by reducing the cost of antiretroviral drugs, thousands and hundreds of thousands of people were able to access antiretroviral drugs against HIV. Up until that point in time, they were just too expensive for the average person or the average country to support, and global efforts reduced the cost of these antiretrovirals to make them available to a much larger population. And then, of course, the two would be global communication through the UN programs through national departments of health, within a country, through the various, for example, in Kenya, the various county departments of health, all reporting to a central area and comparing notes. So hearing what's going on in the rest of the country, as well as communication, not only between the government, but the government and the public about reducing viral spread, reporting disease, disinfecting, using mosquito nets, all of the various health education measures that you know about. All of those, hopefully, their end effect will be to reduce the spread of viral diseases. In the last little bit of my lecture, I want to talk for a bit about viruses and cancer. You'll be hearing more about this, of course, over the course of your medical studies. But when we talk about preventing viral diseases, we're also talking about preventing cancer. Cancer is a major cause of the global burden of disease. Almost 20 million cases in 2020 with 10 million deaths. And surprisingly, the numbers of cancer cases in the world are increasing each year. They are not falling. And there's been increasing over the last several decades, the identification that a number of viruses play a role in the development of human neoplasms. Maybe a fifth of all cancers are associated with viral infections. So when we talk about control of viral diseases, we're also talking about the control of cancer. Here's an example of just some of the viruses that have been linked to cancers. So HPV, you're probably very well that it causes cervical, anogenital, and esophageal tumors. HPV virus causes hepatocellular carcinoma. HTLV1 causes adult T-cell leukemia. And you'll see that only a couple of these viruses, there are vaccines. There's a vaccine for herpes virus, which is being recommended to be given to children before they're exposed to HPV. There's a Hep B vaccine, which is widely suggested for people who are at risk. But this is just an example of some of the cancers and carcinomas and tumors that have been associated with virus infections. Let's talk for a few minutes about Ebola, something that we're very, very familiar with in the news, but it's the belief to occur naturally in animal populations in various countries in sub-Saharan Africa, and it's very infectious, but most importantly, it's very lethal. You will see in history, the first epidemic in '76 in Zaire, there was almost a 90% mortality. Look at these mortality rates, 65%, 53%. There's now an Ebola epidemic happening in Uganda, which I'm sure you're aware of. I just got this off the net a few days ago. As of November 22nd, they have a 40% mortality. That's even though they do have a bit of a vaccine for Ebola now. They have much better treatment, but 19 health workers were infected, of whom 7 died. So this is a very, very serious infection, and an infection when, if it's discovered, there's no question but that isolation, quarantine, all of these measures are not just indicated, but an absolute necessity. Ebola virus has no cure, but supportive care can increase a patient's chance for survival. And there is a vaccine which was developed in 2014, which were fast-tracked into phase 1 clinical trials. This caused a bit of concern because the Ebola vaccine was used in that previous epidemic before it had gone through all of the phases of approval that are usually necessary before a vaccine can be approved for legitimate use. And this caused quite a bit of controversy. It was effective, but it was criticized because it had been used too soon. So this raised issues about the ethics of treating people with vaccines that had not gone through rigorous safety and efficacy randomized controlled trials. The Ebola vaccine was effective, but there was a backlash. I think you can see where this is going to now. because the COVID vaccines were also developed very quickly. They went through rather abbreviated trials, but then were put into effect fairly quickly. But the controversy with COVID was not just about vaccine, but there was a controversy about quarantine, about isolating cases, about social distancing, about wearing masks, about curfews and travel restrictions. All of those techniques for control of viral diseases that were put in place during COVID received strong reactions and a lot of controversy. And of course, because the COVID vaccines were developed so fast, that also meant that rumors developed pretty quickly about them, which in turn exposed the cracks in both the health infrastructure, but also the health infrastructure's ability to respond to emergency situation. But as well, it also exposed the health system's difficulties in educating the public and convincing the public about necessary measures in order to control viral infections. So COVID and Ebola have some connections with each other, if only in terms of how they were used, but also the public reaction to their use. One other final topic that I'm going to talk about is interactions between COVID-19 and HIV. We know that there have been some indications that people who are HIV positive have had some more susceptibility to COVID. But there's also another way of looking at it, and that is that a number of the variants of COVID which developed in Africa. A few of them, like Beta and C12 and Omicron, were first recognized in South Africa and Botswana. And one of the things about the COVID vaccine or COVID vaccinations is that they were targeting people who were immunocompromised in the West. But back here in Africa, there is some evidence that some of these variants may have arisen in people who were immunocompromised themselves. And of course, when you think about immunocompromised people in Africa, you think about HIV. So the question then arises, why were not more vaccinations for COVID available in Africa if that was the place where new variants were going to be arising? There were, people who were infected in 2021, 1.5 million people were newly infected with HIV. But there's probably another 10 million people who remain untreated. A lot of them in sub-Saharan Africa, they're immunocompromised. And so they would not only be susceptible to new variants of COVID, they may be also the source of new COVID infections. So the question, I repeat, is why aren't more people in Africa getting immunized against COVID, not only to protect themselves, but also to produce the effects, reduce the development of new variants. The effects of COVID on HIV, there were a reduced number of HIV tests and viral loads being performed in 2020. Because the health system was overloaded with COVID, treatment for HIV was reduced. And so people, weren't getting their treatment or weren't being treated. And again, TB control was falling apart as well because of COVID. You can see these statistics for TB in 2019, 2020, declining testing, declining people on treatment, a fall in treatment of people who were drug resistant. So all of these, COVID had an effect on HIV and TB, but it could also be asked, what effect did immunocompromised people with TB or HIV have on COVID? And there's a lot of controversy. There was a foreign policy editorial in November 21 about whether the Omicron did arise through the HIV positive people, but not immunizing immunocompromised people certainly did not help to prevent the spread of variants of COVID. So where are we today? Well, more than 12.5 billion cases of doses of COVID-19 have been administered around the world, which means that about 70% of the world's population has received one dose and 64% are fully vaccinated. But then look at these figures from a number of countries in Africa. Rwanda is the only one that is above the world average in terms of fully immunization. And where do we find Kenya? Way down here at 19.4%, which doesn't bode well for the next wave of COVID, which is probably going to be coming through in a few months if it's not here already. And so what's the reason? What are the reasons for this very low rate of vaccination in sub-Saharan Africa? Well, I think you can know the answers. It's what we've been talking about for the last hour. Infrastructure issues, resistance to being vaccinated, problems with the health system, problems with the transport of the vaccine, unavailability of the vaccine, you name it. All of those reasons have been contributing to the very low rate of COVID vaccination in sub-Saharan Africa. And I'm sure we're going to see the consequences of this in the coming months or the next couple of years. But there have been some lessons to be learned from the COVID pandemic. First of all, the fact that COVID vaccine was developed so quickly. Before, we used to think that it would take a decade to develop a new vaccine. COVID showed that we could develop a new vaccine, put it into clinical trials, and have it available in a matter of months. This has changed ideas of what's possible in vaccine development. As well, one of the things about COVID was that rather than trying one vaccine after another, using trials to test a number of vaccines simultaneously in several countries in parallel was one of the ways that we were able to move quickly to expand the trials of promising vaccines, which produced rapid results. Also, it demonstrated that if people really care, there can be money found. Billions of dollars were found in research within a matter of months to find a COVID vaccine. It would be nice if we had that kind of energy and funding to attack some of the other diseases that continue to affect us. Also, COVID demonstrated that public institutions, the public sector and the private sector can work together to create life-saving technologies. But we've seen the mistakes of both public health mistakes and government mistakes that still are being repeated, but we have learned some lessons from the COVID pandemic, which hopefully from a public health point of view can be applied in the years to come. As I said, I will forward this presentation to you. A number of references here that you can look further, but if you go into the internet and Google control of viral diseases, you will find more reading material than you ever wanted. So there's no shortage of material to read. I've gone through things fairly quickly, but a lot of this was probably familiar to you, but I wanted to give you a summary of public health approaches to preventing viral infections, and I hope that was useful. So thank you very much for your attention. We have time for questions. I see a large number of conversations, but it looks like people are just conversing with each other. And people are asking, which country am I from? I'm from Canada. I'm Canadian, but I've lived in Kenya for more than 30 years. So I consider Nairobi my home, but I am Canadian by nationality. That's one question. Questions now. Is there a vaccine for Marburg virus? No, there is not. It's still in the drawing boards. The problem with diseases like Marburg is that the number of cases per year is very small. And so for a drug company to go into the research necessary to produce a vaccine, it's not commercially viable. This is one of the problems with some of these diseases that are very lethal that we would love to have a vaccine for, but the drug company just won't put their money in. So this is an argument for vaccine research not being in the hands of the private sector, but for other reasons. Any other questions? I'm actually, now that I've turned the screen off, I can see hands being raised. If anybody wants to raise a hand, we can actually have a conversation, or you can put questions into the chat box as well. Parainfluenza, no, we do not have a vaccine. We have vaccine for a number of influenza variants, but not one for parainfluenza, not to my knowledge. Don't see any hands. I don't see any questions. Somebody asked a question as to whether I have a daughter. My question to you is, how many cows do you have? Okay, I see no hands. I see no questions. I know you have your exam coming up in a few days. Best of luck to you in that. I hope this has been useful. If there are no more questions or comments, I will close. I will leave and wish you a good day and good luck in your studies. Thanks very much for your attention. Bye-bye, everybody.
Thank you.